你有宿舍嘅咩？係咩？你喺度住啊？哦 ，OK。而家 part time 學生都可以住嘅。哦，係咩？哦，咁正。好啊。好啦，咁我哋開始㗎喇喎。Okay, tonight then we will start a new topic. We call it the diffraction. The diffraction is actually a very common thing that we always need to consider for our design. So part of the material that actually you have learned before. So it actually is a kind of revision, and then we have a part which actually you have not learned before. So the outline is here. We will talk about the diffraction diagram and elastic curve. And then we will talk about the elastic beam theory and the double integration method. And finally, we will introduce the so-called the conjugate beam method. So here is the diffraction diagram and the elastic curve. For the diffraction diagram and elastic curve here, actually this one is very important when you consider your design. So actually, you know, for beam structures, if it is there's a loading, say it is a live load or dead load, then your beam structures will deflect. So the deflection can come from the loading. That means you apply the load to the beam, then you will have deflection. And then because of the temperature difference, then the temperature will also cause expansion and then contraction of your structure. And then for fabrication error, say for example, if it is too short or if it is too long for a member, if you put in a position, then actually it will create internal stress in the structure. The internal stress will also cause settlement or deformation of your structures. And then for settlement, say you have a foundation settlement, pile, uneven settlement, etc. It will cause deflections to your structures. And then for your design, basically we would like to limit this kind of deflection in order to prevent cracking of the attached brittle materials. Because deflection will usually induce stress, and this stress will usually cause cracking or damage to your structure. And if you have learned about the concrete design or steel design, we always mention that the structure should satisfy the ultimate limit state and then the serviceability limit state. For serviceability limit state, that means the structure should not deflect too much or it should not vibrate too much. Otherwise, it will affect the comfort of the building or comfort of the occupants in the building. So deflection is actually very important. So here we will introduce you some idea about the deflection and then the way how to calculate for the deflection. To describe the deflection, usually we will use the so-called elastic curve. Elastic curve actually it means or it sketches the shape of the structure when it is loaded in order to visualize the compute result. And then the elastic curve is actually describe the deflection of the center of the cross-sectional area along the member. And then when the member is subjected to the loading, well, it can have so-called deflection. But when the member is still in elastic stage, that means it will return to its original position when the load is being removed. But when the materials goes into the plastic stage, then actually when you apply the load, it cannot return to its original position. And then in the module here, we will just describe the linear elastic material. That means it is in elastic stage. we will not include nonlinear diffraction here. And then to construct or to estimate the diffraction of the structures. Well, if sometimes it is difficult to estimate, then we can use the moment or bending moment diagram. So we will mention about the way how to use bending moment diagram to estimate the diffraction of the structure. So first of all, you can take a look at for different support condition, then the diffraction will be different. Like for the roller and then for the pin structure, you can see that it will, when the structure is subjected to the load, say for example here, if it is a simply supported beam, when you have a load applied here, then it will deflect like that. So you can see that there will be a theta, will be an angle here for roller support, and then for pin support. But you can see that there are just the rotation here, but there's no deflection. So you can see that the deflection is equal to 0, but there is a rotation at the end of the support. For the pin support as well, there will be rotation, but the vertical deflection will be equal to 0. However, for the fixed support, you can see that both the deflection and then the rotation will be equal to 0. So at the fixed end, actually you will deflect like that. So there's no rotation and then no deflection. And then you compare with the fixed support and then the roller support or pin support, you can see the difference. For fixed connected joint right here, please remember that here is always equal to 90 degrees. And then for pin support, you can see that this one may not be 90 degrees. So when you draw your elastic curve or the deflection of the structures, you may estimate based on this kind of rules. Right here, you can see that when you apply the load, then the structures will bend like that. For negative bending moment here, you can see that it will bend concave downward. So you can see that when you apply the load, as I mentioned, the bending moment diagram will always on the side of compression. So if you have the side like that, then that means the compression is on this side and then tension on the other side. We call this concave downward. For this one, when the bending moment is in the positive side, that means it is concave upward. So it is compression here and then tension on this side. So if you have the so-called the bending moment diagram, you can always sketch your structure deflection. So right here, you can see that it will be something like that. The bending moment diagram will always be on the compression side. Then for here, you can see that we have a location here, the bending moment is equal to 0. It is actually changing from concave downward to concave upward. And then we call that the inflection point. And then the inflection point here, the bending moment is equal to 0. And actually from here, we can estimate the deflection shape of our structure. For the first one, you can see that this one is a pin support, this one is a fixed support. So when we apply the load, we can know that actually for the pin support or roller support, there must be deflection, something like that, because there must be the rotation. And then for the fixed support here, you can see that there won't be any deflection and then there won't be any rotation. So the deflection must be something like that, and then you can join them together. So that's how you can estimate the deflection of your structure. And then for the fixed end, both are fixed end on the both sides. You can see that for fixed end, the both rotation and then the deflection is equal to 0. But in between, it will deform like that. So here it becomes the shape, something like that. And then for the next structure, if you try to rotate it at the ends, then it will move upward. So you can see that it will move upward, and then the beam will go like that. And finally, the bending moment in the last part is equal to 0. So it is a strict part here. So you can sketch your curve like this. And then for this structure, you can see that there's a hinge here. If there's a hinge, that means the bending moment is equal to 0. Then here you can see that this one, just like a cantilever, and here there's no bending moment. If no bending moment, that means this one is a strict part here. And then for here, actually, it is fixed support, so there will be nothing here, no rotation, no deflection, and then finally it will deform like that. And then the remaining part is a strict part. So you can see that for this part, it will be deformed something like that, and then join at the hinge at the B. For here, you can see that your hinge is right here. So for this part, it is just like a kind of simply supported beam. So right here, it will deform like that. And then on this part, actually, it is just like a cantilever. So this point must be at the same point, so it will be here. So if you connected them together, it will be the shape. The first part is the cantilever and then deflect to the point B. And then to here, you will connect to a simply supported beam. And then finally, for this one, you can see that for here, you will deform like that because this one just like a simply supported beam. But on the other side, actually, you have to connect to the point A and then at the point D. So you will deform upward like that. So this is the way how you can estimate the shape of the deformed shape of the diagram or the structure. Okay. And then here it actually describes the way how you can estimate the elastic curve of the structure. And then we have actually done it when I have described the elastic curve. To numerically find the deflection of the structures, we will use the so-called elastic beam theory. For the elastic beam theory, we will assume that there's a part of the beam right here. And then we will consider the width of dx here. So you can see that there's a dx here. We just consider a small part of the element. When we have the small part of the element, we assume that it is subjected to the bending moment M. So there is some derivation to find about some relationship. Rho is actually recorded the radius of curvature. It is found from the center of rotation up to the so-called the neutral axis. It can be shown that actually 1 over rho is actually 1 over the radius of curvature is equal to the epsilon. Epsilon means the strength at this location over y. Y is actually the distance from the centroid up to the location that you are interested in. And then from here, actually, you also have the equation of epsilon equal to sigma over E. Then you can estimate, or you can prove that 1 over rho is equal to m over EI. Now, don't worry, this is just the proof of the equation. And then you may take a look in detail when you are at home. The most important relationship is that we can show that d theta over dx is equal to m over EI. Theta is actually the slope of your structure. And then you can know that dV dx is actually the diffraction of the structure. It's actually equal to theta. So if we differentiate 2 times, you have this relationship. So these 2 relationships will be the most important idea that you need to learn. D theta dx is equal to m over EI, and d square v over dx square is equal to m over EI. Okay, so we will involve a little bit of integration here. Okay, don't worry too much. We will have small part of integration, but the next part of this chapter will just involve normal calculation without calculus. But here we will involve a little bit calculus. Actually, you should have learned before. So right here, you have d theta dx, which is equal to m over EI, and diffraction 2 times, and then you get the values of m over EI. So here is actually recorded the double integration method. So we just have the relationship of dV dx, which is equal to integration of m over EI dx. And then if you want to get the diffraction, actually you need to integrate it 2 times. So that's why we call it as a double integration method. Because before we get the values of d theta dx is equal to m over EI. So if you want to get the diffraction, you just integrate it 1 times. Okay, so you can get the slope by integrating the moment equation 1 time. Then you can get your slope. For diffraction, you can get that d square v dx square is equal to m over EI. So if you want to get a diffraction, you need to integrate it 2 times. Then you can find for the answer. Okay. So for here, if you find for the answer for the rotation, if you got a positive answer, it means that your rotation is in counterclockwise sense. For nu, that means the diffraction, if you got a positive answer, that means the diffraction is going upward. So this is the sign convention for the diffraction and then for the rotation. And then for the integration, after the integration of the equation, actually you have so-called the integration constant. And then you need to use the so-called the boundary condition to find the integration constant. So here we will give you some idea so that you can find for the integration from the equations. And then once you find the theta, I mean the slope first, and then you can integrate once again to find for the deflection. So for here, I will use an example to illustrate to you how to use double integration to find for both the slope and then the deflection of the structure. For here, each simply supported floor joist shown in the photo is subjected to a uniform design load of 4 kN per meter. Determine the maximum deflection at the joist. So for here, actually, we first of all want to find for the maximum deflection. Then we need to find for the moment equation first. So for the beam, do you still remember how to find the moment equation? For the moment equation, actually, you can see that you can assume an arbitrary section X here. Now, you have a distributed load 4 kN per meter here, and you have 20 kN on both sides. So for the first part here, you have the distributed load. And then you have the load 20 kN on this side. So you have your shear and the moment on the other side. Assume that it is a distance X in this location. Then you can find for the moment. So you take moment at this point. So you have the load 20 times X. And then you have your load, which is actually 4X here, and then times the distance X. And then the moment arm is equal to X divided by 2. So you have your moment equation equal to 20X minus 2X squared. Is it okay? And then you have your moment actually is equal to, d theta over dx is equal to m over ei. Or you have d squared v dx squared, which is equal to m over ei. So here is equal to d squared v over dx squared. It is equal to m over ei. So you have this expression. After the first integration, you have first integration constant. After the second integration, you have two integration constant, okay? Because C1 and C2 are the constant that you need to find. Then you need two boundary conditions. Now when X is equal to 0, then the deflection is equal to 0 for this case. And then in the other location here, when X is equal to L, L here is 10 meters. Then the deflection is also equal to 0 because it is a support here. So you have two, we call it the boundary condition. When X is equal to 0, then your deflection is equal to 0. When X is equal to 10, again, the deflection is equal to 0. Okay? Do you know what I mean? Then if you substitute the value x is equal to 0 and then v equal to 0, when x equal to 10 and then v equal to 0, then you can get C1 is equal to negative 166.7. Then you can see that this one is the value. So right here, this is C1. You just find C1 is equal to negative 166.7. And then C2 is 0. So actually this one is C1. Okay. And then for here, you know that the maximum diffraction must be in the center. So you will put x is equal to 5, and then you put it here, 6 is equal to 5. Then you can find the maximum diffraction equal to negative 521 over EI. Okay. And then the next one is that we will have a moment here, m0 applied at the ends of the beam. Then we know that in this case, the moment equation, if we start at x here, then here must be m0. Then this equation is easy because m0 summation of moment is equal to 0. M0 is a negative 1 plus m is equal to 0. So the moment equation is equal to this one, m is equal to m0. So you can see that the moment equation is equal to m0. Then, as I mentioned, moment is equal to EI times the diffraction 2 times. So you just substitute this expression here. Then you have your m0 here. You integrate one time. Then you will get this one actually is the slope. So you have your first integration constant. And then you integrate one more time. Then you have your diffraction. Okay. Then you have C1 and then C2 as 2 integration constants. Okay. Agree? Okay, once you have your integration constant, then you need to use the so-called the boundary condition to find for that. For this beam, you have 2 boundary conditions. One is that when x is equal to 0, then the diffraction is equal to 0. Because this is a fixed support, right? When x is equal to 0, then the diffraction is equal to 0. And then when x is equal to 0, then the rotation is also equal to 0. Because this is a fixed end, right? So right here, this is actually the slope of rotation. When x is equal to 0, the slope is equal to 0. And then when x is equal to 0, the diffraction also equal to 0. Then it's easy, we just put 0 here. This one will be equal to 0. Then we can find that C1 is also equal to 0. For here, when x is equal to 0, then the diffraction is also equal to 0. So we can show that both C1 and C2 are equal to 0. So from here, we can find the so-called slope equation and the diffraction equation like this. M0 x over EI is the slope equation. diffraction equation is equal to m naught x squared divided by 2EI. Okay. If we want to find the diffraction and then the rotation at the ends of the beam, we just substitute x is equal to L. So we just substitute this one equal to L. Then we can find for the answer. Okay. Do you know what I mean? So the positive answer means that it is in counterclockwise rotation. Positive answer for theta A, it will be counterclockwise rotation. Positive answer for VA, it means actually bend upward in the vertical. So for here, you have your answer actually is in the positive sense. That means you bend your beam like that, then it will be something like that. So this is the rotation, theta. This is the diffraction. So the diffraction will be going upward, and then the rotation will be counterclockwise. Okay, do you know what I mean? So after the integration, actually we will have the so-called this expression here, and then we can substitute the value of EI here. And then I can find for the numerical answer for rotation and then for diffraction. Just substitute the values for E and then for the I. And then finally, we can have another example for you. Here you have two parts of the beams here. One is actually supported by the two ends. The other one is just like a cantilever. So you have a force P applied at the ends of the beam. We want to determine the displacement at the point C. Then how we can do that? Now for here, first of all, as I mentioned, to find for the diffraction and then the rotation, actually we need to integrate for the moment equation, right? And then for here, how many moment equations do we have in order to find for the total change of the moment along the beam? So from the first part, we need one function to find for the moment and then for the rotation, or for the moment. The other part, actually from here to here, we need another equation to find for the moment. Okay. So from A to B, we need a moment equation. From B to C, we need another moment equation. So to find for the moment equation, we need the both. So for the first one, you need to cut it as a part. And then for the second one, we also need to cut it as a part. So for the first part, we'll cut it as a function like this. So we take moment at the location here. So we have P over 2 times x1. And then this is the moment equation for the first part. In the second part, we will cut a free body diagram here, and then we consider P over 2x2 because this one is P over 2, and then the length is x2. And then I have a support reaction 3P divided by 2, and then times the distance here, which is actually equal to x2 minus 2a. So this is the moment arm. And then I can find the moment equation px2 minus 3pa. Then to find the deflection, actually I will integrate the moment equation 2 times. So for here, you can see that I will integrate for the first time for the slope, and then second time for the deflection. And then for the second part, I will do the same. Integrate 1 time for the slope, and then integrate the second time for the deflection. Okay. Here you can see that I have 4 constants, C1, C2, C3, C4. I have 4 constants. So I need 4 boundary conditions to find the answer. So what are the boundary conditions that I can use? So for the first displacement here, you can see that when x1 is equal to 0, for here, then the deflection must be equal to 0, right? And then for the location here, x1 is equal to 2a, you can see that the deflection is also equal to 0. And then if you consider x2, you can see that when x2 again equal to 2a, then the deflection must be equal to 0. So right here, you can see that you have 3 boundary conditions. But it is not enough because you have 4 integration constants, right? Then you have 1 boundary condition left. The last one actually you can see right here. At this point, actually this theta is equal to this theta. That means the rotation on the left-hand side will be equal to the rotation on the right-hand side. So it is equal to theta, the B. That means d1 dx is equal to d2 dx. Well, at this location, both x1 and x2 is equal to 2a. Then we will use the 2 slope equation to find for the answer. So this is the first boundary condition that we can find for the values of C2. And then when x1 is equal to 2a, then you can see that we can find for the C1 here. And then when x2 is equal to 2a and v2 is equal to 0, then we can find for the C3 here. And then finally, we can equal the deflection, or I mean the slope on the 2 sides. Then we have an equation here. Because C1 we already know, then we can know C3. Then we can substitute back to C3 to find C4 here. So you have 4 equations and then to find 4 unknowns. And then from that, you can get C1 is equal to PA squared divided by 3. C2 is equal to 0. C3 is equal to 10 over 3 PA squared. And C4 is equal to negative 2 P times A cubed. Then this is the equation for the diffraction. And then we can put x2 is equal to 3a, because right here we want to find the diffraction at the ends of the beam. So for here, we will put x2 is equal to 3a. Then we can find the diffraction here. Then we can see that the diffraction is equal to negative PA cubed over EI. Okay. Then we can use a diffraction like that to find for the answer. But this one actually, if you have taken the so-called the mechanics of material, we have mentioned this method before. So I mean, this part is actually something that you should have learned before. So it is a kind of revision. And then there's a so-called a new method that I can introduce to you. Because before the method actually needs the so-called integration. But for this method, we do not need to use integration to find for the diffraction and the slope of the structure. So you can take a look. For this method, it is more convenient. Okay, so before we go on, just again take a 5 minutes break. Then we can finish the remaining one soon. Okay, just come back 5 minutes later. Okay, then we can continue the new method. Now you can see that we have the relationship like this. Now I think you know the relationship between the distributor law and then the shear. D shear is equal to the distributor law W, right? Then we know that d square m dx square is equal to W, because we know that dm dx is actually equal to the shear. So you can see that we have dv dx is equal to W, and then d square m dx square is equal to W as well. And then from our previous equation, I show you that d theta dx is equal to m over ei. And then we have d square v dx square is also equal to m over ei. So can you see the similarity of these equations? Yeah, you differentiate something, then you can get W, right? Well, here you can also use differentiate theta, you can get something here. So if you see that if the W is equal to m over ei, then actually the shear is equal to the rotation, right? For here, you can also see that if we differentiate something 2 times, it will be equal to something here. And then you can see that if W is equal to m over ei, then the moment will be equal to the deflection. Now, what does that mean? That means if we put W is equal to m over ei, that means the stress at the distributor load is equal to m over ei. Then the shear will be the same as the theta. Then the moment will be equal to the same as delta. So shear and the moment of the beam, for that kind of beam, we call it the conjugate beam. And for these two, we call it the real beam. That means if I want to find the rotation and the deflection of the real beam, then if I have a conjugate beam here, for this, I put the loading is equal to m over ei, then the shear and the moment will be equal to the slope and then the deflection of the real beam. So this one actually is quite interesting. Say if we have a real beam here, and then I have a so-called conjugate beam. The shear of the conjugate beam will be equal to the deflection of the real beam. And then the moment of the conjugate beam will be equal to the deflection of the real beam. So it is something like that. If I have a distributor load applied on the real beam, say for example, I will have a bending moment diagram like that. This is my moment. If I put the W is equal to m over ei, then the shear in this beam will be equal to the slope of this beam. And the moment of this beam will be equal to the deflection of this beam. As I mentioned, when W is equal to m over ei, then the shear will be equal to the deflection. Moment will be equal, shear will be equal to the slope, and the moment will be equal to the deflection. So here you can see that the deflection is equal to moment of the conjugate beam, and then the rotation is equal to shear of the conjugate beam. So this is the theorem. For the real beam, if you want to find the slope, then we just need to find the conjugate beam shear, then we can find for the answer. And then for the deflection of the real beam, then we just need to find for the moment of the conjugate beam. Then we can find for the answer. So you can see that right here, the moment and then the conjugate beam are actually, the real beam is here. Then the conjugate beam is here. For the load, apply on the top of the beam, it will be W here. And then for here, apply on the top of the beam, it will be M over EI. This is the load applied on the beam. Then for the slope, if I want to find the slope, then I just need to find for the shear of the conjugate beam. Then directly they are equal. For the deflection, then this one, they will be the same. Okay. For the moment, you just need to find for the deflection. For the shear, you can find for the slope. But remember, for the conjugate beam, the load would be equal to M over EI. So for here, we need to change our support condition. Because for the real beam, actually, it actually reflects the shear and then the moment of the conjugate beam as well. For the pin support here, the rotation is not equal to 0. And then the deflection is equal to 0. That means for the conjugate beam, the shear is not equal to 0, but the moment is equal to 0. So if it is a pin support for the real beam, it will be also a pin support for the conjugate beam. For the roller support, theta is not equal to 0 because it can rotate, but the deflection is equal to 0. Then the shear, that means it's not equal to 0, and then the moment is equal to 0. So roller support is still a roller support. For the fixed end, actually the roller, the rotation is equal to 0, and then the deflection also equal to 0. If we change to the conjugate beam, actually means that the shear is equal to 0, and then the moment is equal to 0. So it is a free end. And then free end here, both theta and then the deflection is not equal to 0. That means shear and then moment both are not equal to 0. So it becomes a fixed end. And then so on, if you have internal support here, you will change to internal hinge. Internal support here, you will change to internal hinge. If you have internal hinge, you will change to internal support. So to find the conjugate beam, first of all, you need to change the support accordingly. Pin to pin, roller to roller. But if you have fixed support, you change to free ends. If you have free ends, then you will change to fixed support. If you have internal pin, you will change to hinge. If you have hinge, you will change to internal support, and so on. Is it okay for you? So you will need to convert the support condition first. Here I will show you an example how to change the real beam to the conjugate beam first. Now this is the real beam. And then you can know that if you apply the load here, then your bending moment diagram will be something like that. This is 20. I mean, the shear is 20 and the moment is 100. So this is the bending moment diagram of the real beam. Now for the conjugate beam, actually you need to first of all turn the support. This is fixed end. As I mentioned, from fixed, we need to change the free end. So this is free end, and then from the free end, you need to change the fixed. So this is your conjugate beam. And then the loading will be equal to W will be equal to M over EI. So this is your loading here. It will be equal to 100 over EI. This is the loading applied on the beam. Okay. So if I want to find the rotation and the deflection at this point, that means I need to find for the deflection and the moment at the ends. Shear is equivalent to the rotation, and the moment is equivalent to the deflection. Okay. So for here, I have this beam. I want to find the shear and then I want to find the rotation. So for here, after I find this is my conjugate beam, because this is my moment and then I just divide it by EI, then I will subject it to a stress of, the distributed load of 100 over EI. Then I will find for the shear, and then I will find for the moment. And then from here, you can see that the total load is 250 over EI. And then 250 over EI minus VB dash. Then you can see that your theta B is equal to VB dash is equal to 250 over EI. And then substitute the E and the I here. And then you can find for the deflection, theta B. And then for the moment, again, if you take the moment at the ends here is equal to 0, then you can see that your moment arm from here to here is equal to 8.33. So you have 250 over EI and then times the distance, 8.33. Then you can find for the moment is equal to 2083 divided by EI. And then you substitute the values of EI here that you can find for the deflection is equal to negative 21.9 mm. So you can see that your deflection is a negative value. That means you can go down here. And then for the theta B here, you also have a negative here. That means it is in a clockwise sense. So you can have your deflection is rotating in a clockwise manner. Okay, both your deflection and then your rotation is in a clockwise and then in a downward direction. Okay. And then for the next example, we want to find for the maximum deflection of the beam. For this, well, if you want to find the maximum deflection, then that means for the conjugate beam, we need to find for the maximum moment location, because deflection is equivalent to the moment in the conjugate beam. If you want to find the maximum moment, then the shear at that location must be equal to 0. So for here, we need to find for the conjugate beam first. So it is a pin support here on the left-hand side, and this is a roller support on the right-hand side. Okay? So if like that, actually you have a pin and then you have a roller support. Then for the conjugate beam, it will be the same here. You have a pin on the left-hand side, and then you have roller on the right-hand side. Because pin will go to pin, and then roller will go to roller. And then if you have 8 kN here, then actually your bending moment diagram will be something like that. Because this is your bending moment equation. And then your conjugate beam will be something like that as well. And then this is the loading on the conjugate beam. And then from there, actually, the moment is equal to 18. Then for here, actually, you can see that the load is equal to M over EI. So it is 18 over EI. If you have the load here, you can solve for the support reaction is 45 over EI on the left-hand side, and then it is 63 over EI on the right-hand side. As I mentioned, you need to find for the maximum moment for the conjugate beam. That means you need to find for the maximum deflection for the real beam. If you want to find the maximum moment, then the shear should be equal to 0. So you may imagine that there will be some distance here, then your shear will be equal to 0. So here, how to find the shear is equal to 0? Well, because actually it is 18 over EI here, so you can see that, assume that this is somewhere, this is 18, and then for this distance x, it is the value that we don't know. Then the total distance is equal to 9 meters. Then from here, how you can get that? Actually, it is simple. You just use this question mark over x. Then actually it is equal to 18 divided by 9. Then the question mark is equal to 2x. So right here, if this is question mark, then this is equal to 2x. That means the distance here, or the magnitude here, is equal to 2x. Because it is an EI diagram, so it is over EI, okay? So we want to find the x so that this shear is equal to 0. So this is the support reaction 45 over EI goes down. So you have 45 EI going down, which is a negative value. And then this is a triangle. So it is 2x over EI, and then times the x here, and then divided by 2. Because the shear here finally will be equal to 0. So you can find that the location where the shear is equal to 0 is equal to 6.71 meters. So you know that at this location, the moment is the maximum. Then you will try to find for the moment at this location. Because you know that this distance is equal to 6.71. So you will find the moment at this location. So you have 45 over EI times this 6.71. And then you have this triangle. Actually, the area is equal to this one. This is the area of the triangle. And then this is the moment arm. One-third times 6.71. And then from this equation, you can find for the maximum moment. And then the moment you can find that it is 201.2 over EI. And then this moment is actually equal to the maximum diffraction. And then from here, you just substitute the values of EI. And then you can get the maximum diffraction here is equal to negative 16.8 mm. Then you can get the maximum diffraction. Is it okay for you? So do you think that this one is easier than the previous one? Because you just change the beam, the real beam to the conjugate beam. If you find the shear, then you can find for the rotation. If you find for the moment, then you can find for the diffraction. Okay? So actually it is the same that you have done before. And then for here, we have another example to show you how to find for the diffraction at the center C. Well, you can see that for here, you again have a pin support and then have a roller support on both sides, okay? So the conjugate beam will also have pin and then have the roller support on both sides, okay? And then again, you will want to find the diffraction at the point C that you need to find for the diffraction at the point C. Then you just find for the bending moment at the point C for the conjugate beam. So here, first of all, you need to find for the conjugate beam. So as the real beam is a simply supported beam, your conjugate beam is also a simply supported beam. So this is your bending moment diagram, 200, 240, and 200 here. As you know that your conjugate beam will be M over EI. So you just use the M and then over EI here. But you can see that the EI at the center is double than that at the side, okay? So right here, the center, you need to have the EI to be double. So this value is double. So you can see suddenly the stress here goes down like that. Because at the center, actually the EI is double. It's larger. So actually you can see that your stress or the distributed load like that. And then right here, if you want to find the diffraction at the center, then you need to find the moment at the center. And then for this load, you can see that actually you have one triangle here, and then you have another triangle here, and then you have a rectangle here. And then again, you have one triangle here. You have triangle here. And then you have your rectangle here. You cut the free body. And then you try to find the bending moment. Okay. Now, if you cut the free body, then you can see that you have this low 620 EI, and then times the distance, 6 meters. You have 400 over EI here, and then you times the moment arm here, 3.33. You have 200 over EI here, and then times the moment arm here, 1 meter. And then you have 20 over EI here, and then times the EI 0.66 here, or we can call that 0.67. Then you can find your moment is equal to 2173 kNm cube over EI. And then you substitute the values of EI here. Then you can find for your deflection, 40.2 mm. Okay. So here again, you just find the moment at the center. Then you can find the deflection at the center. Okay. You know what I mean? So this one actually you can see that it's quite straightforward. Once you understand the idea, it is simple. You just from the moment you find for the deflection, the shear you find for the slope. Okay. And then here we comes to our last example tonight. So right here you can see that there's a beam, compound beam here, and it's subjected to a point load 40 kN, and then the N is equal to 50 kNm. So we want to find two things. Find the displacement at the point at the pin at the B. So this is the deflection at the B. We want to find the deflection here. And then the slope of each beam segment connected to the beam of the compound beam. And then we also find the delta B here, and then we want to find for the theta B on both sides. Okay? So for the conjugate beam, we want to find for the moment at the point B. And then we want to find the shear on the left-hand side and then shear on the right-hand side of the point B. Okay? Now for here, first of all, we need to change the real beam to a conjugate beam first. First of all, we have a fixed end on A. We have a fixed end here. Then for the fixed end, we need to change it to the free end. So we will change it to the free end here. For internal hinge, we will change to internal support. For pin support, we will change also to the pin support. Okay. Is it okay for you? Then right now we need to find what is the loading applied on the conjugate beam. So for here, first of all, it combines of several things. So for the original beam, we have the case here. This is 40 kN. And then I have a moment, 50 kNm here. So actually, I can decompose it to two cases. First of all, is for the 40 kN apply at the top. And then for the last case, actually, it is the case here. I will apply 50 kNm here. So for the first 40 kN, then I can apply the load here. It becomes a bending moment on this side. Actually, it is 160. And then for this case, if I have a point load at the end, then when I analyze the structure, this is 50 kNm. Then for balance the load, I must have a point load here, which is equal to 10 kN, because the distance here is equal to 5 meter. So the 5 kN times this 5 meter, they can balance each other. But this is due to the moment only. At the same time, I need to have my 10 kN here to balance the force. And then for action and reaction here, if I have 10 kN here, I must have 10 kN pointing upward. Then I will have my moment here. Because actually you can see that this is 8 meter, so I will have 8T on this side. So I will have my bending moment like this. So the overall bending moment on this side will be something like that, which is 8T on this side and then 50 on this side, okay? So you can see that if I have a bending moment like that, I can decouple. Now this triangle is actually this part here. And then this 80, you can see that this is 130, this is 50. When I add this together, it is equal to 80. And this is negative 50 here. When I add this one and then this one together, it is equal to 50, right? So I actually use one triangle and then one rectangle. When they add them together, it becomes the bending shape like that. So you can see that it is a triangle plus a rectangle here. I just add the two together. Okay? Do you know what I mean? Now, why I need to change the moment diagram to one triangle and one rectangle? Because actually it is easier for me to calculate the result. Because triangle area is easy to find, and then I can find the centroid easily. So right here, if I find the deflection at the point B, then actually I just need to find the moment at the point B here. Then from here, actually, I want to find the moment at the point B. Then I actually cut the free body diagram and then take a look to the MB dash. Then it is the deflection. And if I take a look to the shear on the right-hand side, that will be actually the rotation on the right-hand side. So for here, I will take a look to the rotation. So I will take a look to the shear. I consider that all the loads pointing upward as positive, so VBR is the shear here. And then the triangular area is equal to 125 over EI. And then the rectangle here is equal to 250 over EI. And 2 over EI here is the support reaction. I can find that the rotation on the right-hand side is 127 over EI. And I substitute the value and then I can find for the rotation. And then for the same free body diagram, I can find for this MB dash. Then I have this 125 and then times the centroid 1.67. And then I have this 200 over EI times 2.5. And then I have this 2 over EI times 5 meter. Once I find the moment, and then actually it is the deflection. So actually it is equal to 119 mm. And then finally, I can find for the shear on the left-hand side. Remember, if it is on the left-hand side, I have to include this support reaction because it's on the left-hand side. For here, I don't have the support reaction because this is on the right-hand side of the support. On the left-hand side of the support, of course, I need to include this support reaction. And then I can find that the VBL is equal to 0. That means the rotation is equal to 0. Okay. But for this, actually, I suggest that you may take a look at home first. And then you need to know how to convert from the real beam to the conjugate beam. And then you need to how to know from how to find the moment. And then the moment will become the loading applied on the conjugate beam. And then from the conjugate beam, you find the shear actually equal to the slope of the real beam. And then you find the moment actually is equal to the deflection of the real beam. Okay? Okay, so here I will stop the recording first. OK， 咁咧就今日呢堂去到呢度。咁首先各位有冇咩問題？嗱第一次聽咧就可能唔係太熟嘅，咁咧你可以翻去睇下先。咁你有問題咧可以上堂嘅時候問啦。咁我哋下一次都有啲 exercise， 即係大家可以一齊做下先，即係熟習下嗰個情況。咁我哋先繼續落去嘅。有冇問題？OK， 如果冇問題咧，今晚到呢度先啦。咁我會將測驗嗰個時間咧，我會打喺個 Moodle 度。OK， 咁咧測驗前都同各位溫下書先嘅，好嘛？咁各位都即係有個準備啦，好嘛 ？OK， 咁今晚到呢度先啦。咁各位都辛苦啦嚇，好記住啊，11月5號啊。OK， 拜拜。